let's get introduced with the 1D fluid flow. A fluid that flows inside a pipe along its length, say in that direction, is called a 1D fluid flow. It could be a pipe like that of length L. There are 5 conditions that we study or we consider while finding the stiffest matrix and solving for the 1D fluid flow problems. First of all, we're considering an ideal fluid, so the ideal fluid equations apply in here. The fluid is in a steady state, so the transient effects of fluid flow are not considered here. Also, we're not considering viscous flows, so this is inviscid fluid. And the fluid of our interest is incompressible, like water, and like air, which is compressible. And we're only considering a linear flow of fluid, so no rotation is considered in these problems. In fluid flow, stiffest matrix relate the nodal fluid flow rate to nodal potentials. So the nodal fluid flow rates is equivalent to nodal forces in structural mechanics, and nodal potentials is equivalent to nodal displacements. So these potentials are essentially the degrees of freedom in here, and nodal fluid flow rates are basically the loads or forces. And while we do the discretizations and when we draw the free body diagrams, there are 2 conventions that we take into account. Inward fluid flow rate is positive, and so is the potential, and outward fluid flow rate and its potentials are negative. So here, F1x and P1x, which are going into the element, are positive. F2x and P2x are negative because they're moving outside the element. For each element, we can write a velocity vector going from element 1 to element 2. But for each node, we can also have a velocity, which we showed with a star. And that's because velocity happens due to the gradient of pressure. So it's basically an element variable, such as stress and structural analysis. But we define velocities due to Darcy's law when we want to find the relationship between forces or fluid flow rate and potentials. We can also have local coordinate systems per element, as shown in green here. Now, in order to move on with finding the stiffest matrix of a fluid flow rate, we need to define a potential function. A potential function is an assumed function or an assumed solution for the potential along the element. And it's similar to displacement function in structural analysis. Over there we had displacement function, and now we're working with potential function. And potential functions are usually shown with Greek letter phi. We have 2 degrees of freedom and 2 boundary conditions. So at x equals 0, we have P1x, and at x equals L, we have P2x. So we can write a first order polynomial for phi of x, which is equal to C1x and C2, or plus C2. And then we can move on to apply the boundary conditions to find values for C1 and C2. If we do that, we say phi of 0 is equal to P1x, so P1x is equal to C1 times 0, which makes this 0, plus C2, which means C2 is equal to P1x. At x equals L, phi is equal to P2x, so P2x is equal to C1 times L plus P1x, and so we find this value for C1. And as a result, this is our potential function. Again, we can rearrange it to have the coefficients of P1x and P2x so that we could write that in the matrix format like this. So potential function phi of x hat is equal to 1 minus x hat over L, and x hat over L multiplied by this 2 by 1 potential vector. And again, n1, which is 1 minus x hat over L, and n2, which is equal to x hat over L, are called shape functions, as we studied before in structural analysis. So we have 2 shape functions which have the same parameters or same properties as they had in the structural analysis. At x equals 0, n1 becomes 1 and n2 becomes 0. At x equals L, n1 becomes 0 and n2 becomes 1. And the summation of n1 and n2 is 0. So we have found the shape function Next, we can move on to find the stiffest matrix of a 1D fluid flow problem.